Very good morning and warm welcome one and all. So basically in the last videos and as far as the previous articles and examples are concerned, we have understand that mechanical components which are subjected to only one types of loads are considered. That is, for example, the mechanical component was subjected to a tensile stress, or a mechanical component was subjected to a compressive stress, or a mechanical component was subjected to a bending moment which creates a bending stresses sigma b, or a mechanical component was subjected to a torsional moment mt, because of which torsional shear stresses were created. We have also understand the mechanical component which was subjected to the eccentric loading, and we have converted that eccentric loading into the direct loading along with the couple, from which we were getting a resultant stresses. So basically in all these cases, the mechanical component was subjected to only a single loading. But again, there are many components in the mechanical design which are subjected to several types of loads simultaneously. Several types of load simultaneously, that is at a time. Let us consider an example of a transmission shaft. Now transmission shaft is subjected to a bending as well as the torsional moment at the same time. So basically the stresses induced in the transmission shaft will be bending stresses as well as the torsional shear stresses at the same time. Okay, so in the design of such components like transmission shaft, it is necessary, it is very important to determine the state of stresses under this condition. Under this condition means what? Whenever the loading is a combined loading, or you can say the particular mechanical component is subjected to the combined stresses or a combination of loads, because of which the combined stresses are created. So to understand this, the study of principal stresses are very important. Now in the strength of material, you have already studied the basic concepts of principal stresses, and also what are the formulations required for the principal stresses. So here we will just do go on doing the review of the principal stresses and how it is helpful to us in the particular machine design along with the theories of failure, right? So basically what you have studied is that principal stress is nothing but the resultant of normal as well as the shear stresses. So basically these principal stresses are classified into the two groups, normal stresses and the shear stresses. So the resultant of normal and shear stresses are nothing but the principal stresses, which is a very simple definition. So to understand more, principal stresses tells us what is the maximum normal stress, and or you can say that a maximum normal stress, that now normal stress is denoted by sigma x, sigma y, sigma z in the x, y and z direction. So principal stresses tells us what is the maximum normal stress sigma x max or sigma y max or sigma z max in the x, y direction a body can have, as well as the minimum normal stresses a body can have. So from this what we can understand, we come to know exactly how much stress the object can experience, how much stress the object can experience and what at what angle. So now we can compare this stress with the allowable stress or a design stress, and we can understand how the material of a particular mechanical component is going to perform at a given condition. So this is what the principal stresses help us to understand. Now basically, let us consider an example of a simple element of a plate, as you can show in this figure. I am showing with the help of the pointer. So let us consider an element of a plate which is subjected to the two-dimensional stresses. Now you can see this particular plate is subjected to the tensile stresses sigma x on sigma x and the tensile stresses sigma y. So sigma x in the x direction and sigma y in the y directions. Okay. Now along with this tensile stress, you can also see that this particular element is subjected to the shear stresses tau. So tau xy and tau yx, right? Now basically, first of all, let us understand about the normal stresses. Now normal stresses are nothing but the sigma x, sigma y or sigma z, which are acting in a x, y, z directions respectively. Now basically, what about the sign convention? Tensile stresses are considered positive and compressive stresses are considered as a negative, right? Uh, Now basically next comes the shear stresses. Now shear stresses are denoted by tau. So as you can see into this particular figure, the shear stress can be written as tau xy or tau yz. Now basically what is this tau xy or tau yz? You might have already studied the strength of material. I am just giving you a short conceptual information. Now basically when you say tau xy or tau yz, okay, so there are two, you can say, notations x and y which are assisted with the tau. Now basically this first subscript x indicates the area over which the stress acts, and the second subscript indicates the direction of the shear force, right? For example, if you consider this tau xy, here x indicates the shear stress is acting on the area which is perpendicular to the x-axis, and y indicates the shear stress is acting in the y direction. Okay, so we have already proved that the tau xy is equal to tau yx. So these are nothing but the two groups, normal stresses and shear stresses, okay, which are nothing but the two groups of a principal stresses, right? So now basically let us understand the next concept of a Mohr circle. Now one of the most effective methods, Mohr circle is one of the most effective methods to determine the principal stresses and principal shear stresses. So construction of Mohr cycle diagram is very effective method to determine these principal stresses and principal shear stresses, right? You can call it as a graphical method which is used for the representation of the, you can say, stresses, a representation of its stresses. Now basically you can see into this figure, this is a Mohr circle. First of all, we'll understand how to construct this particular Mohr circle, and then we will understand the concept of principal stresses, that is a normal stresses and the shear stresses. Okay, so basically now you might have understand that whenever the loading is a combined loading, like the example of a transmission shaft, okay, we have to calculate the principal stresses, right? So to understand, to represent the stresses and to calculate the principal stresses, we can use this Mohr circle method, which is very easy and a graphical method, right? So now basically the first of all, you have to plot the following points. Okay, so first of all you can say that whenever you are plotting a graphical method of a Mohr circle, okay, first of all let us understand what are the conventions which are used to construct the Mohr circle. Okay, now first of all the normals, let us consider sigma x, sigma y, these are nothing but the normal stresses, okay, and sigma 1 and sigma 2, these are nothing but the principal stresses, right? Now if you look into this figure, first of all we will construct this x-axis. Okay, on x-axis you can find a sigma, and on y-axis you can find a tau. Okay, now this normal stresses sigma x and sigma y, right, we are considering a two-dimensional stresses, so we are not considering sigma z, we are considering only sigma x and sigma y. So now sigma x and sigma y, which are nothing but a normal stresses, as well as sigma 1 and sigma 2. Okay, so sigma 1 is nothing but the maximum you can say principal stress, and sigma 2 is nothing but the minimum principal stress. Okay, so sigma x, sigma y, sigma 1, sigma 2 are plotted on this x-axis, right? Okay, now the tensile stress is considered as a positive and the compressive stress is considered as a negative. So this is a sign convention. Okay, so since tensile stress is considered as a positive, it is plotted to the right of the origin, and the compressive stresses, which is considered as a negative, it is plotted to the left of the origin. Okay, so that is all about the x-axis. Now you can see that the shear stresses, now what are the shear stresses? Tau, that is a tau xy and tau yx. Okay, and the principal shear stress is nothing but a tau max. So tau max is nothing but a principal shear stress or maximum shear stress. So these are plotted on the ordinate, that is a y-axis. Okay, now you know the already you have studied in the strength of material what is the sign convention for the shear stresses. Now a pair of a shear stress is considered as a positive if they tend to rotate the element clockwise. A pair of a shear stresses is considered as a positive if they tend to rotate the element clockwise, and negative if they tend to rotate it anti-clockwise, right? To understand the sign convention, you can see into this figure. Let us consider this tau xy and tau xy and tau xy. Okay, so these are nothing but the two opposite pairs of shear stresses acting on this particular element. Now if you look at these two opposite shear stresses, tau xy and tau xy, okay, so from this particular figure you can understand that this tau xy and tau xy are trying to rotate this element in which direction? In an anti-clockwise direction, right? So they are considered as a negative. And this tau yx and tau yx, now these are trying to rotate this element into the clockwise direction, so they are considered as a positive. And sigma x is considered as a positive, that is a tensile, and compressive is considered as a negative compression, which is plotted to the right side and the left side, that is in positive and a negative approximately. Okay, so this was all about the sign convention. Now once you have understand the sign convention, let us construct the Mohr circle. So basically, first of all, OA bar represents sigma x, that is a normal stress in the x direction. OC bar represents sigma y, that is a normal stress in the y direction. Then AB bar represents tau xy, shear stress. CD bar represents a tau yx, right? Now, now you can join the line D and B. So whenever you are joining a line D and B, you are getting an intersection point with the x-axis called, you can locate it as a E, right? So now you can construct a Mohr circle diagram with E as a center and dB bar as a diameter, and you will get a circle which is called as a Mohr circle. Okay, now once you get the Mohr circle, now you will get a 2 points. The one is the F point over here and second is a G point over here, right? So this F and G represents the maximum and minimum principal stresses sigma 1 and sigma 2. So sigma 1 is nothing but the maximum principal stress and sigma 2 is nothing but the minimum principal stress. And I have already explained you that this principal stresses are nothing but the resultant of normal and the shear stresses. So from principal stress we can understand what is the maximum normal stress or a minimum normal stress a body can have. Okay, so that is already I have explained into the at the starting of this particular video. Okay, so basically now you are getting a sigma 1 and sigma 2, and now again you are also getting a 2 points. This is a H and I on the vertical axis. So these 2 points H and I, this H and I represents the two principal shear stresses, which is nothing but a plus minus tau max. So the above the horizontal axis it is a positive, and below the horizontal axis it is a negative, it is a minus tau x. Okay, so in this way, with the help of Mohr circle diagram, you can measure or you can find out the maximum principal stress and minimum principal stress along with the principal shear stress or maximum shear stress, that is nothing but a tau max. I hope you have understand how to construct the Mohr circle. Now once you have constructed a Mohr circle diagram, now with the help of this Mohr circle diagram, you can easily you can say derive the formula for sigma 1, that is a maximum principal stress, sigma 2, that is a minimum principal stress, and maximum shear stress, that is a tau max. And these formulas or these equations can be used in the design where there is a combined loading. Okay, so first of all, from Mohr circle, sigma 1 is equal to maximum principal stress, sigma 2 is the minimum principal stress. So this we have already understand. Now let us now we'll use some basic geometrical concepts. Okay, so now sigma 1, if you look into this figure, look on the vertical axis, x axis, this vertical axis. Okay, so here you can see that now sigma 1 sigma 1 is equal to OE plus EF. Okay, by mistake I have written here OE plus OF, but it is not OE plus OF, it is OE plus EF, that is a sigma 1. Okay, now so if you want to calculate derivation for the sigma 1, you have to first of all find out the equation for the OE and equation for the EF. Okay, now from the geometry of this particular circle, sigma x is nothing but OE plus EA, right? sigma x, that is a normal stress in the x direction is nothing but the OE plus EA, right? And sigma y is nothing but the OE minus EC. OE minus EC, you will get a sigma y. Now what you can understand from this figure, that EA is nothing but the EC. So EA and EC, these two are equal, right? That is why with the help of the intersection point E and taking a dB as a diameter, I have drawn the circle. So EA is equal to EC. Now if you do the addition of sigma x plus sigma y, what you will get? OE plus EA plus OE minus EC, but EC is nothing but the EA. So I am, instead of EC of sigma y, I am writing here EA. Okay, so EA and EA will get cancelled. So you will get sigma x plus sigma y is equal to 2OE. So from this you will get OE, that is for sigma 1 you should know what is OE plus EF. So the first part I have derived, what is that? Sigma x plus sigma y upon 2. So OE is nothing but sigma x plus sigma y upon 2. Now once you derive the EF and add along with the OE, you will get a equation for the sigma 1. Very easy. Okay, so again here comes the Mohr circle. Now to calculate the EF, let us consider one, you can say EF is equal to EB. Now EF is nothing but EB, right? Okay, so if you look into this particular geometry of the figure, you can understand that EF is equal to the EB. But what is EB? Now EAB or AEB, this is a right angle triangle. So you can apply the Pythagoras theorem and you will get EB is equal to square root of EA square plus AB square, right? So if you find out the equation for the EB, you will get a EF and you can add it along with the OE and you will get a sigma 1. Okay, that is a maximum principal stress. Now what is AB square? AB square from the figure tau xy square, right? Now what is AC? First of all, AC is nothing but the EC plus EA. Okay, and also AC is nothing but the OA minus EC. So I can write AC is equal to EC plus EA as well as AC is equal to OA minus OC. So left hand side is equal, so right hand side will be equal. So EC plus EA is equal to OA minus OC, sorry. But again EC is equal to EA. If you consider this length AC, it is divided into the two parts, EA plus EC. So EC is equal to EA, right? So you can put here in this above equation. So EC, if you put EA, so EA plus EA becomes 2A, and OA minus OC is nothing but a sigma x minus y. So you are getting EA is equal to sigma x minus y upon 2, right? Now EB is equal to EA square plus AB square. So AB square is equal to tau xy square and EA square is nothing but the sigma x minus sigma y divided by 2 bracket square. Now you put everything into this EB. Once you get the EB, you will get EF. Okay, so again here comes the Mohr circle. So now EF is equal to EB. Putting in the equation, you will get square root of sigma x minus sigma y by 2 bracket square plus tau xy square. Okay, now what is sigma 1? OE plus EF. You can look into this figure again. OE plus EF is nothing but a sigma 1 maximum principal stress. So sigma 1 is equal to OE is nothing but a sigma x plus sigma y by 2 plus square root of so and so. Okay, so this is with the help of this equation you can calculate the maximum principal stress, that is a sigma 1. So here you can see from this equation how to calculate the sigma 1. Now what is sigma 2? Sigma 2 is nothing but a minimum principal stress, and this minimum principal stress is nothing but the sigma 2 is equal to OE minus EG. OE minus EG. So when you minus this OE, EG from this OE, you are getting a sigma 2. Now EG is nothing but the EF, right? EG is nothing but the EF. So sigma 2 is equal to OE minus EF. Now sigma 1 is equal to OE plus EF, sigma 2 is equal to OE minus EF. So here there will just be the change in the sign. So sigma 2, that is a minimum normal stress, is nothing but the sigma 1 plus sigma y by 2 minus square root of so and so, right? So now I have got the equation for sigma 1 as well as the sigma 2, and now the third one is nothing but a tau max, which is also called as a principal shear stress or maximum shear stress. Now tau max is nothing but a EH. Tau max is nothing but a EH. Okay, so from E to H on the vertical axis, this is nothing but a tau max. So tau max is equal to EH. Now this EH is equal to EF and EF is equal to EB. And what is EB? EB is nothing but the square root of this. So tau max is equal to plus minus. If I consider the point I, it will become a minus. For point H, it will become a plus. So we'll get tau max is equal to plus minus square root of so and so. Okay. So in this way, with the help of a simple graphical method, by constructing a Mohr circle, I can calculate the principal stresses, that is a maximum principal stress sigma 1, minimum principal stress sigma 2, as well as shear stress tau max. So now whenever there is a combined loading, you can use these formulas of sigma 1, sigma 2 and tau max in case of the designing of a mechanical component. I hope this concept is clear. So in the next lecture, I'll be explaining you what are the different theories of elastic failure. Okay, and so thank you so much for today's.